So I wanted to introduce a little bit of radioactive decay. I'm going to give you the decay equation, the half-life equation. But what I really want to really kind of briefly talk about, and I'll talk about it more later, is radiation. What is actually happening. So in some cases you have yourself an isotope, which means that it has more neutrons than it needs. It has a stable number of neutrons and a stable number of protons. Now if the protons change, that means that the particle is going to move further up the chain. So if you think about carbon 12, or let's say carbon 13, and it has one additional proton, or it's not carbon, it's now 7, or it's moving further and further up the chain. It's got 7 electrons, which doesn't make it carbon anymore, so it's not carbon. So you can't have an additional number of protons to be an isotope, but you can have additional number of neutrons. And when you introduce that neutron, that particle, that atom, is happy with a particular configuration of neutrons. Okay, not only by the sheer number of neutrons, but the order in which those neutrons are being in that system. Okay, so there are some cases where the object is stable, but its neutron configuration is not what it needs to be, and in those cases it has a little bit too much energy and readjusts itself, forming another bond with another proton or another neutron to give up that energy. Or in some cases it has too many neutrons and it has to eject particles, radiation, in order to get that stable orbit. Okay, so that's our situation. Now the idea is that when you talk about alpha decay, you're ejecting particles. Okay, so alpha being this symbol. So when we talk about alpha decay, we're talking about ejecting particles into a system, or ejecting particles out of that atom. Well, it's not just a single neutron. That neutron is bonded to other particles. Actually, in this case, it's bonded to two protons. Well, it can be bonded with more than 2 protons, but it's bonded here, and it ejects. So what it ends up doing is it rips a section of that atom away from the system. So away from that atom. So it rips out a big chunk of it. Well, not figuratively, but it rips out this chunk of that particle. So when we talk about alpha decay, we're removing 2 protons and 2 neutrons. Okay, so when alpha decay happens, it's a massive object. It's a huge object. 2 protons, 2 neutrons is pretty big. Okay, you're basically talking about a helium particle at that point. And in some cases, alpha decay is expressed as this. Okay, because we don't keep track of the electrons when we talk about nuclear decay. So it's ripping off 2 protons, 2 neutrons, and it's being ejected. Okay, so that's alpha decay. It's a massive particle. So when we talk about later about some diagrams, Feynman diagrams and cloud chambers, you can tell the difference between alpha decay and other types of decay because it's a massive particle and it's positive 2. Okay, so you're ripping out 2 protons, 2 neutrons in order to experience this alpha decay. So it moves the particle down the periodic table. So if you had carbon, let's say, which has 6 protons, you're moving it down the periodic table by 2. It no longer has 6 protons, it now has 4 protons, making it a completely different element. So alpha decay moves it along the periodic table. Okay, cool, that's alpha decay. Now the next type of decay, sorry, I'm looking at my notes, is beta. Beta decay happens, and beta decay is actually kind of funny. When beta decay happens, you have a neutron. So we know that neutrons are stable particles. So a neutron has no charge. Okay, but the configuration of that atom is that it would be more beneficial if it increased the number of protons. So what you do is you take this neutron, Okay, you take this neutron and you eject a particle from the neutron itself. It gives out a particle, and when it gives out that particle, it changes the property of that neutron. So when it ejects a particle, it's ejecting this electron. Okay, it gets rid of a negative charge. Well, using conservation of charge, which is a conservation, that means that this neutron had a positive and a negative charge inside of it. So when it ejects the negative charge in the form of an electron, it becomes positively charged. Now, because electrons have almost no mass, we consider them relatively massless. There are certainly things that have less mass than an electron, and a neutrino being a perfect example of this. So it gives off this electron, but because this electron has very little mass, this neutron loses almost no mass. So this new proton here is about the same mass value. It doesn't really change it, but it's gained this positive charge. So it gives off this electron and becomes a proton. Okay, moving it up the periodic table. So it has two mechanisms there. So you can create something by generating an alpha particle, giving off this 2 proton 2 neutron, and it might not like that configuration. So it can say, well, I got this neutron that and I want to move back up one to get a little more stability. So it can give off an electron, making it so here it is. It goes through alpha decay. It can move down 2 points down the ladder. It loses 2 protons. So it moves up. It moves down that periodic table. It moves back up it, I should say. Okay, so it moves, down the. It loses 2 protons, so it changes its element. It's now a smaller particle, a smaller atom, and then boom, it can experience beta decay, which takes one of the remaining neutrons and turns it into a proton, moving it back up. So you go back 2 spaces, you draw that card that says you move back 2 spaces, and then it can move back up 1 space, or it can move up 1 space. So it moves up 1 space and then back 2. It has this flexibility to move all over the periodic table, depending on the type of radiation it generates. This alpha allows it to move back 2. This beta allows it to move up 1. So you have this freedom in order for an object to move. Well, it turns out that radiation has this natural tendency. It's moving towards a point. So radiation is always heading towards iron, and in order to do it, it uses these 2 types, these 2 types of radiation in order to move towards iron. Once it achieves iron, it's relatively stable. It's really interesting how iron is this stable particle in the nuclear. When you look at nuclear physics, it's stable. Everything is approaching iron. The cool thing about it is when you talk about suns and the reaction, the sun is burning up fuel, and it's burning up fuel trying to achieve iron. It's taking hydrogen, producing helium. Helium is splitting up, producing hydrogen. But in the process of doing that, it's making other elements doing that, moving down to iron. Okay, once the sun has consumed all of its nuclear material, all of its hydrogen, its helium, and then on to cobalt, and on and on and on and on and on and on and on, approaching iron. Once it's achieved iron, it consumes all that material in a really short period of time. It consumes all of that iron and whatever other elements it may have. Well, actually, it consumes it into different forms, but once it's burned up all of its hydrogen and helium, it's gone down to this form, and those materials, oxygen and all that other stuff, is consumed really quickly into iron. So the sun quickly turns into iron, and boom, it explodes. Okay, so that's when you get a nova. It shifted all of its material. It's used all the useful material and hydrogen and helium into these heavier elements. Well, once it's got to that point, it's moving down that periodic table. It takes those heavier elements and consumes them, moving them further down the periodic table, moving them further down that periodic table, till it reaches iron. And iron is like stable. It doesn't want to move. There's not a nuclear reaction that wants to take iron and convert it into something else. So it explodes into these novas, Well, in the action of exploding, it's producing a tremendous amount of energy. That tremendous amount of energy then, boom, populates the universe. It expands it out. It's just spreading it over there. And it actually will convert the iron, because of the amount of energy, into other elements. But the sun itself is heading towards iron, and once it hit iron, it explodes into the nova. The nova spreads out, and you've got all these other particles that are being created in that massive explosion. So everything on the periodic table is being produced in this reaction. You start off with hydrogen and helium, terribly simple particles. I mean, hydrogen is just one proton and an electron. Helium is 2 protons, 2 neutrons, and 2 electrons. So there's a nice little combination there between the proton, neutron, proton, neutron. Well, actually, proton, neutron, neutron, proton. You got this little bond here, and then you got 2 electrons, one going this way, with the other one going the opposite direction. You got that going on, and those are incredibly stable. But it requires nuclear reactions to move further up that periodic table. But once those reactions are exhausted, once you reach iron, which is stable, it explodes. And then all the other elements are being produced after that explosion. Okay? Really kind of cool. But anyway, those are 2. The third type is gamma. Gamma radiation. So you have protons and neutrons that are inside the nucleus. We call those nucleotides. But the configuration of those is an unstable configuration in some cases. Your protons and your neutrons, they're not this perfect ball, and it's not really it's probabilities. So you may have some finger pointing out, or some kind of weird configuration, and it would be preferred if that configuration changed slightly. So in order to do that, it produces another form of energy. It gives off some energy to make it stable, and that's gamma radiation. Now, proton or alpha decay produces a +2 charge. Beta decay produces a -1 charge, an electron. This produces a helium particle. This produces an electron. Gamma decay has no mass. It's nothing more than light. But that light is being generated in a nuclear reaction. Okay, where normally the light is just being exchanged from energy levels in an electron. Gamma radiation is completely different, as it's being formed in a nuclear reaction. That's why when we look at gamma radiation, we're looking at a nuclear reaction going on. There's a reformation of those neutrons and protons. So you may have something happen where you're ripping a huge section out of an alpha particle, and then it will want to realign itself. So it can produce gamma radiation afterwards to try to realign that particle to make it the lowest possible energy state. So you'll produce gamma radiation. The gamma radiation is nothing more than light. Okay, so those are your 3 types of energies, and those are the 3 types of decays. Now we're going to talk about the decay rate in the next video, because I'm running out of time.